Welcome back. In this section, we discuss Carnot's theorem. Statement of the Carnot's theorem. No engine can be more efficient than a reversible Carnot engine working between the same two temperatures. All reversible engines working between the same two temperatures have the same efficiency. In order to prove Carnot theorem, consider two engines. One is Carnot engine R, then a irreversible engine I. Here Carnot engine is a reversible engine. This Carnot engine absorbs heat QH from the high temperature reservoir, then performs work W, then it rejects heat QH minus W to the low temperature reservoir. The efficiency of the Carnot engine is given as eta R is equal to, efficiency of the Carnot engine is given as eta R is equal to W divided by QH. Then consider next a irreversible engine I. An irreversible engine I absorbs heat QH dash from the high temperature reservoir and performs work W, and then rejects heat QH dash minus W to the low temperature reservoir. Efficiency of this engine is given as eta I is equal to W divided by QH dash. Then according to Carnot's theorem, the efficiency of reversible engine should be greater than irreversible efficiency of irreversible engine. Eta R should be greater than eta I. But in order to prove this theorem, we take an assumption that assume that the efficiency of the engine I is greater than that of R. That is, here this is only one assumption, eta I is greater than eta R. Then eta I is given by the equation W, eta is given by the equation W by QH dash greater than W by QH. Then QH will be greater than QH dash, that is QH minus QH dash greater than 0. QH minus QH dash is positive. The engine, next section, the engine I drives the Carnot engine R backward as a Carnot refrigerator. The engine and the refrigerator coupled together in this way constitute a self-contained machine. From this figure, it is clear that here the engine, here the irreversible engine I works a reversible engine R. It performs an external work on refrigerator R, so that the Carnot reversible engine becomes a Carnot refrigerator. That is, this Carnot refrigerator, this refrigerator absorbs QH minus W heat from the low temperature reservoir, and a work is done by the irreversible engine, and QH amount of heat is given to a high temperature reservoir. Together the system act as a refrigerator. The net heat extracted from the low temperature reservoir is, from this figure it is clear that first here QH dash minus W, here QH minus W. Therefore, the net heat extracted from the low temperature reservoir is QH minus W minus QH dash minus W is equal to QH minus QH dash, which is positive. It is already found that QH is greater than QH dash, hence QH minus QH dash is positive. And this is same as the net heat delivered to the high temperature reservoir. That means the net heat delivered to the high temperature reservoir is equal to net heat extracted from the low temperature reservoir without doing any work. So, it clearly violates the second law of thermodynamics. Second law of thermodynamics states that heat cannot be transferred from a low temperature reservoir to a high temperature reservoir without doing any external work. Since this device violates the second law of thermodynamics, our original assumption that eta I greater than eta R is false and Carnot's theorem is proved. Thus, the result is eta R is greater than or equal to eta I. That is, efficiency of a reversible engine is greater than or equal to efficiency of an irreversible engine. Next, the corollary of the Carnot's theorem can easily be proved. All Carnot engines operating between the same two reservoirs have the same efficiency. In order to prove this theorem, consider two reversible engines R1 and R2 operating between the same two reservoirs. If we imagine R1 driving R2 backward, then Carnot's theorem states that eta R1 less than or equal to eta R2. Here R1 drives R2 backward. Then if R2 drives R1 backward, then eta R2 less than or equal to eta R1. So, it is not possible. Therefore, it follows that the efficiencies can only be equal. That is, eta R1 is equal to eta R2. Efficiency of first reversible engine will be equal to efficiency of a second reversible engine. Next, we discuss the thermodynamic temperature scale. 0th law of thermodynamics establishes the basis for the measurement of temperature. From the 0th law of thermodynamics, we get the temperature difference, but an empirical temperature scale must be defined in terms of the thermometric property of a specific substance. A temperature scale that is independent of the nature of the working substance, which is called an absolute or thermodynamic temperature scale. The efficiency of a Carnot engine depends only on the temperature of the source and sink. That is, we already proved that the efficiency of a Carnot engine is given as 1 minus T2 divided by T1. Here T2 is the temperature of the low temperature of the reservoir, which is at low temperature, and T1 is the temperature of the reservoir, which is at high temperature. The Carnot engine provides the basis for the thermodynamic temperature scale. A Carnot engine absorbing units of heat QH from a reservoir at a high temperature TH and rejecting QL units of heat to a reservoir at a lower temperature TL has an efficiency eta R, that is independent of the nature of the working substance. That is, here we given as eta R is equal to 1 minus QL divided by QH. The efficiency depends only on the two temperatures of the reservoirs. Efficiency of a reversible engine is a function of two temperatures TH, TL, where phi of TH, TL is an unknown function of the two temperatures. Here we get eta R is a function of two temperatures TH, TL. Then 1 minus eta R is equal to 1 minus phi of TH, TL. From the equation, eta R is equal to 1 minus QL by QH, we get QH by QL is equal to 1 divided by 1 minus phi of TH, TL. And this can be written as a new function f, new function f of TH, TL, where f of Th comma TL is also an unknown function of the two temperatures. Apply this equation to the 3 Carnot engines operating between the 3 reservoirs where T1 greater than T3 greater than T2. From this figure, T1 is one temperature, T3 another, T2. T1 greater than T3 greater than T2. Here 3 Carnot engines are there, RA, RB, RC. RA is the Carnot engine which operating between the temperatures T1 and T2. RB operating between the two temperatures T1 and T3. RC operates between T3 and T2. Here the Carnot engine RA absorb Q1 amount of heat from this reservoir and doing a work W, and it reject Q2 amount of heat to the temperature to the reservoir which is at T2 temperature. Then the 3 temperature for engine RA, Q1 we can write Q1 by Q2 is a function of T1 comma T2. Since the heat Q3 rejected by the second Carnot engine RB is absorbed by the third Carnot engine RC, both engines working together are equivalent to the first Carnot engine RA. That means here RB and RC, these two engines are working as a third engine RA, thus absorb the same heat Qi from the reservoir at T1 that engine RA absorbs. So for engine RB, Q1 by Q2 is a function of T1 and T2, then it is equal to Q1 by Q3 is a function of T1 and T3. Engine RA rejects heat Q2 to the low temperature reservoir. So engine RC must also reject heat Q2 to the low temperature reservoir. This is clear from that figure. So for engine RC, Q3 by Q2 is equal to a function of T3 and T2. Q3 by Q2 is given as Q1 by Q3 by Q2 by Q3. It's from this figure, from the above equation, f of T1 comma T2 is equal to a function of T1 comma T3 and function of f of T2 comma T3. This T3 is the temperature which we arbitrarily chosen, and since it does not appear in the left hand member of the above equation, T3 must be dropped out of the ratio on the right. After it has been cancelled, the numerator can be written psi of T1 and the denominator psi of T2, where psi is another unknown function of temperature. So from the above equation, Q1 by Q2 we get, dropping T3 terms, we get T1 by T2. Thus the temperature on the thermodynamic scale are to each other as the absolute values of the heats absorbed and rejected, respectively by a Carnot engine operating between reservoirs at this temperature. Thus the Carnot engine supply the universality that is lacking in the ideal gas temperature scale. Finally, the thermodynamic temperatures are called absolute temperatures because they are independent of any material. Thus the thermodynamic temperature scale is defined so that the ratio of the thermodynamic temperatures of the two reservoirs is equal to the ratio of amounts of heat exchanged among these reservoirs by Carnot engines working between their temperatures. The ratio of thermodynamic temperatures is independent of the nature of the working substance and depends only on the property that is common to all substance. That is, here the thermodynamic temperature depends only on the nature of the working substance. Temperature measured on this scale are in Kelvin. The efficiency here is again eta is equal to 1 minus Q2 by Q1. 1 minus Q2 by Q1 is equal to 1 minus T2 by T1. When Q2 equal to 0, the efficiency of the engine is unity. Thus 0 of the thermodynamic scale is that temperature of the sink at which no heat is rejected and all the heat is taken from the source is converted into useful work. Here the thermodynamic scale, the absolute 0 is the temperature at which all heat is rejected to the sink. That is, the whole heat absorbed from the source is rejected to the sink. No work is done here. So, a temperature lower than absolute 0 is not possible, as it would imply the efficiency of the Carnot engine would be greater than 1. It is not possible. The ratio of 2 Kelvin temperatures is the ratio of 2 heats that are transferred during 2 isothermal processes bounded by the same 2 adiabatic curves. The 2 adiabatic boundaries may be located experimentally and the heats transferred during 2 isothermal nearly reversible processes can be measured with considerable precision. This is one of the methods used in measuring temperatures below 1 Kelvin. To complete the definition of the thermodynamic scale, assign the arbitrary value of 273.16 Kelvin to the temperature of the triple point of water TTP. Here the triple point of water is taken as 273.16 Kelvin. For a Carnot engine operating between reservoirs at the temperatures T and Tp, we have the efficiency of the Carnot engine is given as eta is equal to 1 minus Q by QTP. From this we get the relation Q divided by QTP is equal to T by TTP. From this it is clear that the temperature T is equal to 273.16 Kelvin, that is QTP into Q divided by QTP. For a Carnot engine operator between reservoirs at the temperatures T and TTP, here where TTP is the temperature triple point, we have Q by QTP is equal to T by TTP. T by TTP, here triple point, then T is equal to Q into TTP by QTP, where TTP is equal to 273.16 Kelvin. 273.16 Kelvin into Q divided by QTP. 1 degree, from the above discussion we can define 1 degree. 1 degree is defined differentially as the difference of temperature between 2 isothermals, one of which is at the triple point of water bounded by a pair of adiabatic between which if a Carnot engine operates, the work done per cycle is 1 by 273.16 of the heat absorbed or rejected by the engine along the isothermal at the triple point of water. Then we have to go the relation between absolute scale and perfect gas scale. In order to derive the relation between absolute scale and perfect gas scale, consider a Carnot engine that absorbs Q1 heat at T1 on the gas scale and lambda 1 on the thermodynamic scale. Here T1 is the gas scale and lambda 1 is the absolute scale, temperature in the absolute scale. then Q1 by Q2 is equal to T1 by T2 is equal to lambda 1 by lambda 2. This equation is from the Carnot cycle equation, showing that the ratio between any two temperatures on the thermodynamic scale is same as that between the two corresponding temperatures on the perfect gas scale. The ratio will be same. When lambda 1 is equal to 0, then T2 equal to 0, that is 0 of the thermodynamic scale is identical with the 0 with the gas scale. The efficiency of the engine operating between a given pair of temperatures, say T1, T1 plus 100 on a gas scale, and lambda 1 and lambda 1 plus 100 on absolute scale should be same. Then eta can be written as, in the gas scale eta can be written as T1 minus T1 plus 100 divided by T1, and in the absolute scale the equation becomes lambda 1 minus lambda 1 plus 100 divided by lambda 1. Then indicating that T1 is equal to lambda 1. Thus, the thermodynamic scale is in perfect agreement with the perfect gas scale. Let me conclude the session. Today we discuss the famous Carnot theorem, then we prove the Carnot theorem. Next we discuss the thermodynamic scale and the relation between the thermodynamic scale and perfect gas scale, and we define 1 degree, then what is 1 Kelvin, etc. Hope the session was beneficial for you. See you next time. Until then, goodbye.